So the next chapter deals with gas power systems. It's a long chapter. It's probably the longest in the textbook because it has compressible flow, it has gas turbines and propulsion systems, like a jet engine is a gas turbine on an aircraft, as well as reciprocating internal combustion engines, the otto, like gasoline engine, and the diesel, like a diesel engine. So a lot of times you can split them up. This, we're going to start with internal combustion engines. Here's a picture of, just pop the hood and take a look, right? Internal combustion engine. Every now and then you should check the oil. When you look at them, they're a little overwhelming at the beginning, are they not? How many people have been into engines? Yeah, and they're even getting more complicated because of the sensors and electronics, and you can't hardly do anything now without a code reader. You should get familiar with the major parts of engines. Let's say this, it looks like a V engine. It has a spark plug, spark plug, spark plug. It looks like 3 spark plugs on this side. It looks like a spark plug. Or maybe there's 4. I'm trying to count them. And then, so it may be a V6 engine. Or you may own a V8. Or you may own an inline 4. Some people even probably have a 3-cylinder engine. The newer small, really small, high efficiency cars are 3-cylinder engines. So how many people know how many cylinders are in the engine that they own and drive primarily? Okay. So what is it, a 4? 6? Anybody have more than 8? I doubt it. Anybody have fewer than 4? How many people have a motorcycle? How many in the motorcycle? 2? 2? Who has a motorcycle? 2? So I encourage you to pop the hood, learn, point at things, understand them, as well as maybe take it apart. But if you pull one of these engines, which some people I'm sure have pulled out of cars, it takes equipment, engine hoist, and it's very dangerous. You could lose a finger if the thing drops, slips, falls, whatever. Very heavy. But you can also take apart a lawnmower, and you can learn a lot about a lawnmower. It's very simple, but it has all the basic components, right? And what happens that end the life of a lot of lawnmowers, they have a tree stump or a rock or a boulder, and the blade twirling around in a circle, right? Going like this, with a 12-year-old, 10-year-old, brand new, being trained to cut the lawn, but the dad forgot or somebody forgot to tell him, oh, watch out for that tree stump. And many a new lawnmowers done. So what'll happen, this will get bent, the crankshaft will get bent, then it's pretty much a toast. You can replace it, but it's a pain. So the crankshaft from the top up here is a flywheel. Connected right in here is a connecting rod to a piston. A lot of times the pistons slide forwards and backwards this way. And in the front, there'll be a little wire going down to the spark plug. And so the piston's going back and forth horizontally, and it's creating the rotary motion of the crankshaft, and that drives the blade connected to that crankshaft. Okay. You can find them cheap. Find them when people bust them and then throw them away. Find them old. You can find them on trash piles. So in our neighborhood, down the street once a year, spring or fall, they'd have big item pickup. It's a great time to learn. Free education waiting for you. Just go out and get that lawnmower off of your neighbor's trash pile quickly. Why? Because the metal recycle guys are running the neighborhood in circles like vultures, and it's money for them, and they will pull all the metal off because they can recycle it. And there's a lot of aluminum, especially in lawnmowers. So you have to beat them. And then when you're done taking it apart and learning, put it right out the curb. It won't last an hour, and it'll be gone. And the person that puts it in the back of their pickup truck will thank you because it's all broken down and easy, okay? So this is one of these where you could take it apart and don't even try to put it back together. So just look for big item pickup, but you have to be quick. Okay, you'll probably need this. You may have to break something. Big hammer. Be careful. And electric impact will really help, unless it's relatively new. Then you can just get them off. Otherwise, you can get a friend and do it together because it's hard to take those things apart. You can diagnose and see, oh, that's why they're getting rid of this here lawnmower. See, they hit that something so bad it bent that blade. A lot of times when you take it off, this is the top of that crankshaft right here. And up here, this is the large flywheel. In the large flywheel is a lot of inertia to get it through all four. Three of the strokes don't produce power. One of them consumes a lot of power or work, and that's the compression stroke. Only one stroke produces power of the four-stroke cycle. So 3 times you're not doing anything. You've got to get money out of the bank, right? You get money out of the flywheel, the inertia. Anyway, there's a little key right here, and a lot of times when you hit something, it may not bend the blade, it may not bend the crankshaft, but it slips right there. Now your timing's off. And this one doesn't look too bad, but I've seen them sheared the whole way. So you have to pull that flywheel off the top, put a new little soft metal pin in there that's supposed to fail instead of breaking something else. That's the function of that little key. And they cost 99 cents. So you could learn a whole bunch about fixing lawnmowers and repairing them and how they work. But what I wanted to do is I wanted to show you some stuff, because out on the internet, it's just incredible what's available out on the internet for visualization. Years ago, you couldn't watch. I never had a video. I mean, I was through my education and everything, PhD, before the internet was invented. Hard to imagine, right? But you can watch, this is put out by Briggs & Stratton about engines and the utility and where they go. There's plenty of them. But one of the things it does later on is it describes the basics of what's happening. Maybe I should have let it run without my playing with it. Talking about air valves opening and closing. Typically on a lawnmower it's running horizontal, right? That piston sliding back and forth horizontal. And the rocker arms, sometimes they have them with a little push rod right here. Whoops, I just messed that up, didn't I? I can't draw on that. Here's 4 essential elements: air, fuel, compression, and spark. A lot of times it's like, check those. Do you have good airflow? Do you have fuel? If you don't have fuel, you're not, pull all you want, it's not going to run, right? A lot of times the carburetor is all balled up, gummed up after sitting for a long winter season. And you just drop the bowl, clean it, and then put it back together, and it works. So they're going through the intake stroke, ingesting air-fuel mixture. The piston's going down, and then at the bottom dead center, the intake valve will not be open anymore, but it will transition to be closed. Up here is a mechanism with this push rod, little rocker, and down below is a camshaft controlling the valves. Then you go through the compression stroke. At the top, you get a spark plug. Did you see they showed a little spark coming up to the spark plug? Kaboom. You have combustion. It's spanking hot, high pressure, high temperature. It's the pressure that pushes the piston down. As it's pushing, it's expanding. That's your one stroke where you get work out or energy into the system, into the power. And then at the bottom, you have to open up that exhaust valve, and the piston's going to return in the exhaust stroke. So it's when that exhaust valve cracks open, there's a big rush of exhaust products out. Plus, you're pushing. At the top, this valve, the exhaust valve, has to close. The intake valve has to open. And then you go back to the 4 strokes. What was the first stroke? Intake. Second, compression. Third, power stroke. Fourth, exhaust. So that's your 4 strokes. You can do it in a 2-stroke engine. It's a marvel. It's a genius engine, clever design, but let's just cover the 4-stroke. So here it's showing you the 4 strokes. Boom, 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 boom. Thank you, Briggs & Stratton. They do good work. Also, if you do get something off the trash pile, there's videos that just show you how to remove the engine. And so I just thought I'd quickly show that the engine sitting here, that piston, that's a spark plug, and the piston's running back and forth here. All right, he's saying disconnect some cables, and he's going to pull this engine off. All right, he has air impact. Much better, taking old bolts off. And there's comes the blade. And then typically there's 3 bolts, 1, 2, 3, or sometimes 4. Those are metal steel bolts that go into aluminum. A lot of times you just shear them. They won't come off if it's an old This guy got them off. And then it just drops. So there you go. Not much to it, and you can get the lawnmower information about lawnmower engines and stuff off the internet. Let me show you this. This is another video. Somebody took it apart. Here it's got it all taken apart, and he's got the bolts out of the top for the head. The spark plug is sitting in the head, and he's going to lift the head off, and there's a combustion chamber. There's the inside of that spark plug. Hopefully you saw that. It's kind of quick right in there. See right here? That's the spark plug combustion chamber. What it looks like is flat. And then you see two valves exposed. That's the head gasket. You can reuse those on cheap engines, but the larger one is for the intake. The smaller one's for the exhaust. And then this is the piston sliding in the cylinder. He's showing you the L shape. They call it a flat head or L head, L shape. Combustion chamber is right primarily over the intake and exhaust valves, a little bit of that cylinder. The cylinder, piston you can see comes up very flat. So there's a high compression ratio. But typically it's not that high. For this type, it's probably 6-to-1, 8-to-1. It's not like 10-to-1 compression ratio. So that would be on the side, piston sliding horizontally. Up at the top, he reaches his hand in the back and rotates it. That would be like the flywheel at the top. Okay. Let's see. He does a pretty good job of showing you, okay, this is a carburetor tube, connect to the carburetor, the air come in, go sucking in, and then right, if I can pause right there, you can see the stem of this valve right there. And that's the exhaust. So right here, the muffler would be connected. And it's really good if you've never sat there and rotated through, watch the action of the valves and the placement of the piston. If you've done it, that's great. But if you haven't and you're an aspiring mechanical engineer, I really encourage you to take advantage of your neighbor's trash pile or even your own trash pile, or find a neighbor or friend that's got one mower sitting in the backyard. They can't get rid of it. They can't just throw it on the tree. They have to wait for big item pickup, right? They're happy for you to take their trash. And then get an education that's free just by taking it apart. But I warn you that sometimes you need a big hammer or an impact or a friend that has those. Also, when you take these apart, there's oil. So be ready to catch and dispose of about a quart of oil. This is more to it than I need to see, right? For these engines, they're so simple that there's a magnet pickup on the side. I don't know if he's going to show it, for the spark. And it comes around and it actually fires every top dead center. You're at top dead center on the compression. That's when you need the spark. But you're also top dead center at the end of the exhaust stroke, right? It does nothing. But it's easier just to have a wasted extra spark than to try to figure out the mechanism and add to the cost and complexity of the engine. So they throw two sparks, which is rare. Usually you just throw a spark when you need it. So let me move to this illustration, because this illustration I've been showing for a long time and it's very, very useful. What they have is they have a piston and cylinder. It's a dynamic little visualization. This has been out for a number of years. And at the top, see, it goes through different strokes. Right here, that valve, that intake valve just opened, and it's ingesting air-fuel charge. So that's the intake stroke. You can see the position of the crankshaft. Now it's at bottom dead center. Then it's coming back up. The valves are both closed. Intake is closed. It's a compression stroke. That is a little image of a spark plug. It's going to fire right at the top dead. Look at the color change. Boom, red hot, high pressure. Valves stay closed down through the power stroke. So it's coming down. They're changing the color, showing the temperatures decreasing in the pressure. That exhaust valve cracks open at bottom dead center. There's a mad rush out. That's why you have mufflers. It's high Mach 1 right there, high pressure going across that valve. But then you still push out even more exhaust gas. A lot rushes out immediately at bottom dead center, but then more rushes out as you push it out in the exhaust stroke. Then you just repeat it. What's nice about this dynamics simulation is they put up a visualization of the pressure volume diagram to the side. That's pretty unique. And they have a trace, and can you see the little dot running around the red curve? And so you can follow the pressure, what's happening in the cylinder as it's going. So it's the pressure of the gas, which is the pressure on the side of the walls, the pressure on the top, as well as the pressure at the face of the piston. And if the piston's moving, then that's work, boundary work. True? So that's why the PV diagram is so important. So right here, you can see this is the intake stroke. This pressure is less than atmospheric pressure. It's at a state of vacuum. It's having to draw air through some ducting across a filter, air filter, there's a pressure drop, through the intake manifold, through the throttle body, all the way and even across that valve, that small opening for the intake valve. Those are all pressure drops from atmospheric pressure. It's at a state of vacuum in there. Okay? Then it gets, I'm kind of getting out of whack here, but then it gets to the bottom dead center, and it starts the compression stroke. And when it gets to ZZ, spark. What happens? Very prompt combustion. So the pressure skyrockets when it's at top dead center. Then you expand in the power stroke. See the big pressure drop right in this vicinity when it's at bottom dead center? That's due a blowdown. And then you still push, so slightly over atmospheric pressure as you're pushing it out. And you have to push it through the exhaust valve, through the exhaust manifold, through the catalytic converter, through the muffler, through the tailpipe. Finally, atmospheric pressure. And then it drops. So this is a great illustration. Okay. Let's take a look at another illustration. Stop. Some of these are just great. So this is an inline 4. Now that if you can get one pressure, one cylinder and one piston understood, then you just have 4 of them. And they have it color-coded so you can see the power is the orange when you have a power stroke, the combustion at the top and then pushing down for the power stroke on each of them. You have the crankshaft and how that rotates, translating that reciprocating motion of the piston in the cylinder to rotational motion in the crankshaft. These are connecting rods connected to the piston that slides, and they just show you how that mechanism works. Then they have a belt, the timing belt, that goes up and runs 2 overhead cams. So you'll see that overhead cam, 2 overhead cams. And you'll have for each piston 2 exhaust valves and 2 intake valves plus 1 spark plug. I think some have 3 and 2. Anybody know what they have in their engine? They'll be like, oh, I have a 24 valve engine, right? Well, how many cylinders do you have? And so if you had a 6 cylinder, you had 24 valve, 4 valves per cylinder, 2 intake, 2 exhaust. This is just a great, it really clarifies, I think, if you could see it and see it how it moves, and you could speed it up and slow it down. So they've done a great job on these illustrations. I'll show you just another one. Come here. This is a traditional, like Chevrolet big V8. V, why V? The 4 cylinders in another 4-cylinder bank in a V shape. Okay? And this is the block and the crankshaft and the mains to bolt it down. They're just showing you how it's put together. This is upside down, not right side up. They're going to flip it around in a second. And okay, there's that crankshaft. Keep going. There's the connecting rods. And you'll see how they have the connecting rods. 1, 2, 3, 4, 5, 6, 7, 8 connecting rods. Those are the pistons, wrist pin. And you have only one camshaft, an older V8, sitting kind of in the valley. And then they have lifters sitting on them, and then little push rods, long, thin push rods that come up to the top where the head is. There's a timing chain. So connected the the timing for the crankshaft and that camshaft. And typically the camshaft makes 1 rev for 2 revs of the crankshaft. Oil filter, oil pan, and then they're going to put the heads. There's the valves with the little rocker mechanism. And the spring makes the valve seat quickly. That you have to push to open it, but then it wants to return with that spring. It's a poppet valve. The very old traditional head. Oh, look at that, advertising Chevrolet. So like a 350. There's your fuel injectors, a fuel rail, the intake manifold right in here, intake plenum, throttle body. So it's nice to know. And so as you push down on the gas, it opens up those butterfly valves. Yeah, that's it. How could I not think? And so there you go. One thing I want to go to another one too is this is a block. You can see this is all one machined part, right? And mechanical engineers really are our domain. A lot of people, but I wanted to stop right there. Whoops, back up. Right here, what is coming down? Right, these little caps, and then the connecting rod. You see that? See, this is the connecting rod to the piston. What are these half moon on the bottom and top? Bearings. You never heard of spinning a bearing? You take that top half or bottom half, and it's not sitting on the top or bottom half anymore. It gets a lot of slop in there from wear, and then one slips and comes around. So you've got one place where there's no bearing and one where it's doubled up. And that engine goes kaboomy pretty fast because there's a lot of heat generated right there, scoring of the crank. And then typically the connecting rod burst and thrown out the block. This is wrist pins and then the piston so it can wobble. That's the wrist pin and piston. And they put them together inside. And then the whole mechanism, the bolt. That's the flywheel, right? In the back, where the starter runs on those gears, there's the head. And so it can be a lot more complex than a little Briggs & Stratton 3.5 horsepower lawnmower engine. But you can learn a lot from that Briggs & Stratton engine. It's cheap. You can hurt yourself on one of these. Well, there's more time, 2 overhead cams. On this one, more modern. The head gasket went on there and then put down and bolt the head to it, the engine. Notice the difference in the diameter of this sprocket on the crank that the timing chain is going to run on and the diameter up here. And so what happens is this gives you the right ratio of turns. 2 rotations for the crank, 1 rotation for the camshaft. Okay, because it takes 2 crank rotations for a complete cycle. Okay, so there you go. Hopefully that was interesting. Let's go ahead and stop it and jump back to here. So there's a historic distinction between an external combustion engine and an internal combustion engine. All these gasoline engines, diesel engines are all internal combustion. Used to be you burned the coal, boiled the water. That isn't where the expansion happened, so it was piped over, and that's where you had the expansion in the engine. So, and then the beauty of the crankshaft, how it converts the reciprocating motion in the piston in the cylinder back and forth, up and down, to rotary motion, rotational motion. One of the things I challenge students to do is to look at an illustration and then name the parts. Put it away, test yourself. Can you recall all these parts? It's a good way to learn. And so, now I'm not going to do that now, but I encourage you to do that. Take a look at this illustration. Oh yeah, that was that camshaft. And it has a lobe on it, and then it pushes down on the spring and the poppet valve to push it off the seat to open up a passageway for the intake as well as the exhaust. And then you had the spark plug, blah, blah, blah. You can go through the whole thing, okay? Used to be you didn't get to see the visualization like I just shown you. You had to take it from a picture like this or a figure. So we had how many strokes? A 4-stroke cycle. You have the intake stroke, compression, power, exhaust. And then I showed you this illustration. Here's that website to find that illustration. Since it's not on YouTube, So let's do a review of what we covered in Thermo 1. So, well, what is the air standard analysis? Well, you assume it's a fixed amount of air trapped in a piston cylinder apparatus. The air never is converted into combustion products. It's not an air-fuel mix. It's just pure air. It always behaves as an ideal gas. Combustion process is very complex. We just replace it by heat transfer from an external source when the piston's at top dead center. Little acronym, top dead center. When the piston's at top dead center. Okay? There's no intake or exhaust process that we explicitly model. We just say we're going to replace that or model it by having a heat transfer from an external source or to an external source when the piston's at bottom dead center. So that's how we get away with simplifying it enough so we can make an analysis. All the processes are assumed to be reversible. Why do we make this air standard analysis? Because it makes the calculations doable. You also see the distinction cold air standard analysis. Well, it's everything that's above, but also constant specific heats that are evaluated at ambient temperature, either 25 or 300 Kelvin. Why the cold air? It's even more doable. You can do the calculations and see the relationships in the analysis. Let's do a quick review of the Otto cycle. Otto cycle has 4 processes. So from state 1 to state 2, the process of adiabatic compression. Then from 2 to 3, constant volume heat addition. 3 to 4, adiabatic expansion. Then 4 to 1, constant volume heat rejection. So on a PV diagram, start with a large volume, bottom dead center, and put top dead center somewhere like that. Start with low pressure, compress it, the pressure went up. That's from state 1 to state 2. Constant volume heat addition, the pressure is going to go up even more. Then 3 to 4, that's going to be expansion. And then 4 to 1, constant volume heat rejection. So this is Q in. This sometimes I put Q out. This is adiabatic, no heat transfer between process 1 to 2 and process 3 to 4. So that's what the cycle looks like on a PV diagram. What's it look like on a temperature entropy diagram? Start relatively low temperature, state 1. You go through reversible adiabatic compression, isentropic process. The temperature is going to go up. And then constant volume heat addition. The temperature is really going to go up because you're bringing in heat. Your entropy is going up as the temperature goes up. So it goes out like this to state 3. And then reversible expansion from 3 to 4. And 4 is still hot, still high pressure. You have heat rejection. So this is the Q in. This is the Q out. These were adiabatic. So what does the illustration, the area inside the cycle on a PV diagram represent? The network of the cycle. So that represents W net of the cycle. Because what is the work from 3 to 4? That's a positive work. You can do the area under the curve 3 to 4. But what's the work 1 to 2? Well, that's a negative work because it's a compression. It's going into the gas, not out of the gas. And so you would subtract off that to get the difference for the network of the cycle. True? Right. What about on a TS diagram? Area in the curve, area enclosed, Q net, right? Q net. All right, and then the So that's Q net, this area. Take the first law for each of these processes from 1 to 2. Did I write the first law correctly in neglecting changes in kinetic potential energy? But which term is 0? Is Q 1 to 2 0? Yeah. And then from process 2 to 3, that's the first law. Is work 2 to 3 0? Yeah. Is for the process 3 to 4, is that the correct first law? Yes. Which Q or W 0? Q, and then, so all of these 4 are 0. If I sum up this column right here of the W's, these 4 right here, what do I get? Is that work net? Sum of those W's, is that equal to the work net? Yes, it is. And if I sum up this column of Q's, is that Q net? Yeah. If I sum up this column right here, what do I get? 0. Is Q net equal to work net for the cycle? Yes. All right, let me get your exam back.